Thank you very much, Jerry. It's definitely a pleasure to give this talk. Some of you have seen a part of this talk in a quite recent talk that I gave in the European XFEL, but here at least we have the chance to have a bit more questions. So the talk is really divided in two parts, a little bit like what Jerry also asked. So in between parts, you will be able to ask questions. So and it's a bit kind of provocative in the sense that I'm not going to talk too much about methods, even if there is a bit on the method part, how we get there, but actually on using the high resolution X-ray absorption, emission, and then if you combine both the RIXS as a way to solve chemical problems. As I'm a chemist, I'm primarily interested in using these tools to solve problems, not necessarily on the development of techniques, even if some of you know me for some development on the techniques. So without, okay, so what is this? Without too much delays, I mean, we are using X-rays as a way to measure chemistry, and primarily I'm interested in 5Ds and 3Ds elements, which actually are quite ideal for example, doing X-ray absorption and X-ray emission in situ. And that's actually what actually attracted me to start using these techniques, the ability to look at reactions in real conditions, as my background was primarily heterogeneous catalysis. Also the fact that with the appearance of the XFEL, we also can look at these things not only in situ and in real conditions, but also in real time. So that's what actually been the motivation to move into X-ray absorption and X-ray emission. And of course, one way of seeing X-ray absorption from a kind of chemistry point of view is it's a way to probe the empty states. And if you're primarily looking for 5D elements and 3D elements, these are quite ideal tools because you can map the D states, which are going to be directly involved in the reactions that you are interested. And then on the emission side, you are, of course, looking for the occupied states, which is also going to be involved primarily, of course, the valence to core states, but you can also learn things from the core to core transitions. And the question, of course, is how we're going to do this. And of course, most of the people that are in this list will know that if you try to measure emission directly, this is quite broad, so the signal will be very difficult to analyze. So we need a spectrometer. And I've used a couple of spectrometers, the Jochen and the Van Hamos. The talk here will be primarily or it will be only on the Van Hamos side, which is a dispersive type spectrometer that allows you to get basically single shot spectrum. And basically if you scan the beam, you will be able to build the RIXS map. And then we use this for two specific applications that I will talk here. One is atomic telemetry, and this is about trying to unveil the action mechanism of chemo drugs in real conditions. And there is unfortunately a huge need for new chemo drugs. Most of the treatments we have today is run around cisplatin and oxaliplatin, which is a platinum-based drug. They are always quite similar. They are this kind of 4-coordinated platinum planar, and they tend to basically be given to you on the kind of what some people call a prodrug. So not the most active version of the drug, but the drug that then needs to be hydrolyzed in the body. And in part, this is a way to prevent, for example, that drug that goes in the bloodstream starts reacting with everything. But unfortunately, of course, these drugs are not yet selective enough, and that's why we see the side effects that you are normally associated with chemotherapy. Now, the reason why we thought X-rays is particularly good compared with other techniques, for example, vibration spectroscopy, is that you focus on the central element. So you focus on the platinum. And since we don't have that much platinum in our body, unless you had some kind of implant, then you almost like background free. So you sit basically on that central atom and you're basically gonna see what that central atom does. Of course, if the central atom starts reacting with a lot of other components in your cell or in your blood or in your membranes, that will also be picked up. And then you would have to deconvolute this from the data that you measure. And in the case we are using hard X-rays, we can penetrate to, in this case, you could think about your just Empendorf, measure the drug with your X-rays, you can measure the absorption and emission, and then you can keep adding things to it to basically understand how these drugs bind to the body. And just to, before we go to a specific drug that I will talk to you, it's from a chemistry point of view, it's always a bit kind of strange that there is hundreds of thousands of drugs, both of platinum, but also of other elements like osmium and ruthenium. And very often these drugs have let's say, a range of cancers that they attack. And of course, everybody's trying to find something that is more specific than cisplatin for specific drugs. But when it comes to the mechanism, everybody kind of associates the mechanism always being the same thing. You have a water addition to the molecule. This then becomes basically the thing that will bind to very often the DNA and very often in two guanine sites. And I always wonder, like, why would we then have such a difference in action? Because if they use very similar motifs and they work in the same way, then you're just basically playing with very small parameters. That is, for example, kind of permeation into the cell, or actually kind of making sure that the drug gets into the right place to act. That was for me a bit strange, and then also a bit strange, for example, for the FDA, which has stopped clinical trials of new drugs until they actually show that you have a different action mechanism. So we were very interested, for example, on providing this tool to be able to then demonstrate that you can have different action mechanisms, but also done in real time. Cisplatin took almost 20 years to be found that the drug works and how it works and where it binds. That clearly cannot be the way to go forward, so you can speed up the process of getting new drugs into the market. So apart from the spectroscopy, then we can add theory to try to find out how these drugs bind and which side these drugs bind, and then based kind of an action mechanism based on them that can then be exploited to either improve the drugs or to inform, for example, the FDA to take this drug forward to a clinical trial. So we are gonna today talk about platinum 103. We have validated the mechanism with the approach with the cisplatinum, but since this is something that most people are very familiar with, we decided to just, in this talk, to focus on the platinum 103. Now, this is a drug that has been seen for many years as a competitive drug to cisplatinum. It works on cancers that the cisplatinum stopped working, and it's also seen as a less toxic and less side effects. But there was no action mechanism for this. And even the people that developed, which is a group in Monash in Australia, also assumed that once you add this into a physiological serum, it will bind waters to it, this will get into the body, this will then bind to the DNA to two guanines, and that's how you're gonna stop the DNA replication. And that's how this drug will work. So we thought, okay, let's see if this is actually true. So we use our technique, and this is what you see. This is, of course, a resonance X-ray emission spectroscopy of this drug in a neutral kind of solvent, in this case acetone, that prevents that the drug kind of starts reacting. For example, if you put with water, it will already start reacting and changing. You can then do the cuts across the emission lines or across the absorption. You can see a difference between high resolution and low resolution X-ray absorption. And this is quite important because you can see this kind of small, let's see if I can bring my mouse here. This peak here is almost invisible on the normal X-ray absorption. And you will see that this is quite an important show. And also the white line is quite small because platinum is a D9. So then you have basically here a D7 in terms of the oxidation state, which means that if you have changes that are primarily associated with absorption, then you should have a very sensitive tool to do that. And that's why we think high resolution X-ray absorption is a much better tool to look at this type of transitions. So this is how platinum 103 looks if you just measure it in acetone. And this is what it looks when you measure it in buffer. And in buffer, it will supposedly happen, this hydrolysis that people say that happens. Now, if you look at the RIXS, of course, you cannot really see much difference. But if you look at the difference of the RIXS, and you can do this using the Van Hamos because you have this perfect energy calibration. Since we always get the elastic peak, we can always calibrate the energy of our spectrum, and therefore you can then do direct RIXS map difference. And you can see that the difference is primarily located at around the main emission line. That means that it's primarily located the difference on the high resolution X-ray absorption. So we did a cut there and then tried to analyze. So if you do the cut, you see the platinum 03 that is basically in black. Once you hydrolyze it, you have a lower white line. This is also similar to, for example, what you see in cisplatin. Of course, the structure is different, but the changes in the density of states is quite similar. So the first thing we needed to do is, of course, try to understand what is happening. And I told you that in the other drugs, the preferred kind of mechanism is that water gets in, it will basically hydrolyze one or two of the ligands, will coordinate water to it, and this is then becomes the active drug. This is also what was believed by the group in Australia, but we very quickly figured out that this couldn't really be happening because it would actually require stabilization of the charge at the water. Together with the group in Vienna of Professor Leticia Gonzalez, we carried out time-dependent DFT calculations, which could see what is the structure of the hydrolyzed platinum 103 once you put it in physiological soil, both from a thermodynamic and a kinetic point of view. And if you see the profiles in the bottom, which shows only the thermodynamic cut, you can see the path one is the preferred one. It has the lower barriers and is also the most stable of the products. So in the case of platinum 03, you do not actually add waters and replace them, replace a ligand, you actually hydroxylize. So this is a very significant chemical reaction compared with a simple ligand exchange. And when you're doing this, you're gonna be basically hydrolyzing this big bridge side of the molecule and bind two OHs to it. This also is the most thermodynamic, but also the most kinetically favored product. So now we have done the hydrolysis, then the normal thing to do is generally to add DNA. And if you're doing this from a diffraction point of view, then you're gonna be looking for your adducts. And that was the problem with the cisplatinum. It took almost 20 years, Professor Stephen Lippard in MIT, to isolate and crystallize basically an adduct that then was shown that actually it binds to two guanines, and this then blocks the replication of the DNA and therefore kills the cell. So you have your platinum 103, you have it hydrolyzed, and then you just add the DNA. And you see, as soon as you add the DNA, the white light comes up. The changes are primarily on the absorption, as it was in the case of the hydrolysis. So that's why we're only going to focus here on the X-ray absorption. And so if you do the difference, you see there is a peak associated with the addition of the DNA. Now, what we then did is basically add the monomers of the bases and see if we can replicate the changes by adding them. So if you see, if you have the guanine, the signal difference is completely different when we add the DNA. And this was believed to be the binding site of the platinum 103. But if you add adenine, the signal matches very well in energy. Of course, the intensity of the signal is a bit higher since you have isolated bases compared with DNA, which is a lot more complicated, and therefore you have less of these motifs. The other important thing is that the group in Australia had always believed that the backbone of the phosphate would be involved also in the stabilization of this complex. But you see, if you have adenine with two phosphate groups instead of one phosphate group, the signal is similar in terms of difference, but is shifted in energy. So even with this just simple approach where you add the DNA and then you look at the bases and just compare the signal difference between the bases and the DNA, you can already get a very good hint that this drug will bind through the adenine and not with the influence of the backbone of the phosphate group. Now, we had the luck, of course, to be working with Professor Leticia Gonzalez, and then we decided to do the same thing. Measure what is the most favorable from a point of view of thermodynamics, but kinetically binding of the bases to our hydrolyzed drug. And you see, you have on the path one, you have the guanine, which was believed to be the preferential site, and you have on the path two, the adenine. And you can see that it clearly is the adenine site. It's both thermodynamically more favorable, but also kinetically more favorable. And the reason why it's so thermodynamically stable is that actually it forms a kind of a tridentate structure that is very, very stable. It even goes negative in terms of free energy. So it is the most stable product you can form. And this is quite important because if the drug binds so strongly, it means it will not detach. That means it will break the replication of the DNA, and there is a less probability that the drug detaches during the process, which would need to increase the doses and of course create even more side effects than we are associated with chemotherapy. So just to sum up, you have your platinum 103, it gets into the buffer, it hydrolyzes, but it basically does through hydroxylation, and then it binds to the adenine, not to the guanine and not to the phosphates of the adenine. Now, what we know so far from platinum 03 is that we did these studies just with pure DNA, and we of course want to move towards doing this also with cells. Unfortunately, until now in the synchrotron, people always get a bit afraid when we say we're going to bring cancer cells, but this is going to be done. And you can do exactly the same approach because platinum is unique to the drug. So that means you are basically playing with a background-free structure. Now there is similarities, of course, between cisplatin and platinum 103, but the similarities are on the signal, not on the way that the things are actually working. And of course, if you want to do this in a kind of fast and a kind of almost, I would say, high throughput way, you would really need to combine this with theory, because once you get the models, a little bit like we had a couple of weeks back with XAS to compare the model to the signal that you measure is the way to go. The thing to say about atomic telemetry is that it encapsulates everything that I wanted to do when I started doing with X-rays. Basically, it's an in vivo or an in situ type experiment where you really measure the things under the conditions that you are interested in. It's elemental specific, and you use this in your favor. Like I said, if you compare with vibration spectroscopy, where everything will contribute to the signal, is an absolutely nightmare. Here is a completely clean signal from the drug. It's very low background. We did the studies with millimolars of concentration, very, very close to the concentration that people are using on the normal dosage on chemotherapy. You can determine the amount of drug that is bound. That is a simple signal difference between before and after. There is no need for extractions, no crystallization, and label free. And this, of course, has been the biggest drawback of doing diffraction as a way to try to come up with action mechanisms of these drugs. So I just want to finish this part to acknowledge, of course, the people that have helped, apart from the group in Vienna that did the theory, and of course, Jakob and Joanna that helped with the part of the spectroscopy. I have to also thank Biden and Glenn for Monash for the drug that they sent us to us, and of course Martin at the Swiss Light Source.
All right, will you break for questions here?
Yeah.
Okay. Yes. Wonderful, wonderful talk. I've got a few questions for you. Yeah. It looks like you got most of your science out of the HERFD cut.
Yes.
And but there's not a lot of features in the HERFD, even after you do that. It made me wonder if you had tried to do deconvolution on the, I assume, L-alpha partial fluorescence yield.
Yeah, we do it a little bit the other way around. We measure the resonance XAS and the RIXS and look for where the difference are. And we didn't so much difference on this case on the emissions. So if you look on the on this one, this is actually the REX of both of them, the delta REX, basically the difference between the two maps. And you see that it's primarily at the cut of the HERF that you see the difference. So what we did is then we analyzed primarily the HERF. But you are absolutely right. We can also look on things like balance to core. It's just at the moment, what we have is that the signal there is so low and it's so undistinguishable what we are actually looking for, compared with in this case the X-ray absorption.
Yeah, no, I wasn't thinking valence to core. I was thinking about I can't remember the name of the scientist in Japan. I apologize. He's written a number of papers that discusses how you can generate RIXS data if you know the non-resonant X-ray emission and the total fluorescence yield XAS. There's standard formula from quantum mechanics that would let you generate the RIXS plane as long as there are not many body effects.
Okay.
So it won't get things quite right in the pre-edge and maybe even at the white line. And so that got me thinking, you know, you can get something that looks an awful lot like HRFD if you do a maximum likelihood deconvolution on your XANEs.
Okay.
And so I was curious if you had tried that. We've played with that a bit in the past with lanthanides and other elements where the core hole broadening is very large.
Yeah, we didn't. I mean, here, I mean, like I said, having the ability to do this at the synchrotron, there was quite easy to get the full map and do it. But it becomes important when you're going to bring this to the lab, and that's what I didn't mention is we are building these spectrometers in the lab, and there of course running RIXS is tricky. And then this is an approach because you cannot run really HRFT because you don't have a scanning beam. So that definitely is something to look at.
Yeah. The other thing I was wondering is what was the bandwidth that the von Hamos was giving you?
This would be good to have here, Jakob. I mean, we use a 25 centimeter bandwidth, and I think we measure about, I think realistically about 80 EV, but we can get, normally we get about 100 EV.
Okay. Yeah, the reason I was wondering is I was just wondering if you went to a Johansen that was just a little bit off circle, so you were taking a narrower band of the emission, you might be able to get the data even more quickly. Yeah. By focusing the energy bandwidth just at the energies that you care about. But the data is beautiful.
Yeah, I mean, we're gonna try to run this in Max 4 at Boulder to see if when they have the Johansen commission. I mean, we didn't have. We were discussing with Matthias to try to get this spectrometer from SRF, but then at the time I then moved to Sweden and Jakob moved back to Poland, so it became a little bit difficult to do this. But it's definitely you have a point there. I mean, I think in this kind of drug in the end played to be actually quite a well-behaved drug. We have actually working now with the other ones that for of course the Johansen would help us a little bit on that space.
Okay. All right. I don't see any additional questions in the chat, and so you should continue. Thank you.
Yeah. So I now it's going to move completely out of pace in terms of what are we trying to do, and in Sweden I would say apart from a little bit of this work on the chemotherapy drugs, most of my work is on plasmonics, and also when I told in the beginning that I'm not going to talk too much about method development, and of course that always is the case if you do not need to do method development. But we then realized that of course we needed to do method development when it came to measure the plasmonics. So this talk will be a little bit about what we use the X-rays to see on the plasmonics and what we want actually to see going forward. So if you don't know much about plasmonics, it's a very interesting class of materials. It's become a very hot topic of research over the last decade. And primarily is because it has this huge light absorption capacity. So some people say 10 times more, the most, I would say, advocates will say even 1,000 times more than any other material. And this has to do with the fact that as light approaches these nanoparticles, it bends, and that means they have a very high absorption coefficient. So it is much, much higher than actually the geometric side of these materials. And what actually happens is you create a resonance. You basically create a hot gas. This hot gas will start resonating, and then you will create hot carriers through a process called ladon dumping. And after you create the ladon dumping, you have these hot carriers, which are the carriers we want to use if you want to do photocatalysis or solar cells, but they will very quickly relax. And they will have a time, maybe about 1 picosecond, and you can still extract carriers. And that's what you see here on the carrier relaxation. But this basically exponential decay will rapidly thermalize and will basically lead to emission of heat. And when I started this, actually, most people had assumed I had a project with IBM, and most people had assumed that you could not ever extract carriers from these materials. because the process is so quick that basically you will be able to use the heat. The heat, of course, is very high, and the process that we had with IBM, you could generate on the particle something like close to 800 degrees C. So it's an enormous amount of heat that you generate on a particle. But I always thought that at least we should be able to prove that you form hot carriers and that they are actually delocalized, and that there will be a chance that some of them will be extracted. So actually we use X-rays to prove this. And in terms of applications, if you want to put it from a plasmonic point of sight, what are people trying to use this in chemistry, is basically you have three, I would say, fields. You have the people that are trying to use the heat associated with this. This is very localized, very specific heat that you can somehow also tune based on the properties of the materials you put there, because the absorption and, let's say, the extent of plasmonic is associated with the morphology of the particles. For me, I'm interested very much on what people call the electronic part of plasmonics. So the use of the hole and the electron both at the same time or independently to drive either chemistry or to produce solar cells. And there's also a possibility to use this as a kind of an antenna type process where you can actually shift the molecule that gets absorbed on the surface to a different electronic level. For example, in this case, it is moving the adsorbate from a singlet state, injecting into a kind of a triplet state. And this then forces the reaction to go in a different process. And Professor Lineage in Michigan is been leading this part. And most people are focused either on the thermal or on the electronic part. The other good thing is that these materials are quite easy to do. I mean, any metal will have a plasmonic resonance. The ones of interest are the gold group metals, so gold, silver, and copper, because it absorbs on the visible domain, and also aluminum. They are generally, if you are, of course, the gold group metals, the stability does decrease when you go from gold to copper, but they are fairly stable. They are very easy to tune. I mean, in a sense, you can change the particle and you will absorb any part of the spectrum. And this is, of course, quite difficult if you associate it with molecules or semiconductors are alternative light absorption. And like I said, the other thing that drove me to it, it was when we were working with gold, is that it is particularly difficult to do oxidations in photocatalysis. I mean, not to say that at the moment we produce, for example, in water splitting, a lot of hydrogen, but that process is becoming more and more efficient. But the oxygen evolution is still lagging behind. And when you're driving photocatalysis, you cannot just consume one type of charges. You have to consume both. And you have to consume both at the same time. That means if your oxygen by default is already much harder to do because it's a different number of charges, different kinetics associated with it. But you have problems in actually stabilizing this intermediate oxidation products that need to be there, then you are in trouble. So that's what drove me into try to move into this. So the first thing was we needed to prove that you actually have an electron in a hole at some point in time generated. And we went back to our preferred technique that at the time, that of course was X-ray absorption. At the time, we were not even yet making RIXS map to see if you see changes in the electronic states. And if you think about high resolution XAS, and in this case, you really need to do high resolution XAS or HERFT, if you want to call it, because your gold X-ray absorption on the 5D is very, very low because you have almost no empty states. In fact, it should be a 5D10. The only reason why you don't have a 5D10 is because of the nano size. You have a small hybridization with the X6SP, and that opens a little bit of the D states. That also has been associated why gold becomes catalytically active when it's below 10, 15 nanometers. But basically, you are measuring a very low signal. So if you try to measure this just using the normal Xayness, you will not see any difference. But if you measure this when you're doing in high resolution XAS, and you do the experiment as we have it here, so you have a continuous X-ray and a continuous laser, and you do light on and light off, and then you do the difference. You can see through the difference, there is a clear kind of this very typical derivative type signal that is associated with the creation of hot electrons. That means that you are affecting the empty states, And this empty state is basically changing over time. Now, this is the good part. The bad part is if you were measuring this on the sensitizer, you would know exactly what the signal is, because you can only put it, the electron in a very specific place, like on the edge of the conduction band, on the semiconductor, on the LUMO states of a dye, for example. But the plasmonic is a resonance. So we could actually fit the signal by, for example, putting a lot more electrons into the 6s and less on the p, or put more on the p. So this is the problem with plasmonics, because the electrons will basically have an energy distribution. They will be occupying different states, and there is so many electrons being excited at the same time that you can never treat it as a single photon, single electron process. That also made us go back to that original picture, that this middle part, while it's kind of accepted that it's happening, there's no evidence that it's happening. And there is even people that have claimed, like for example, Liam, that said that if you want to extract charges like we normally do, we put it in a semiconductor. The study that I showed before, we also show that you can put the electrons into titanium, and quite recently into gallium nitride p-state. So you can take electrons and holes. But the mechanism has always been associated with hot carriers. And Jan, for example, says that no, that you can actually induce this process directly on the semiconductor. So that means you don't actually gain anything from this, because this lives for so low period of time, and that it relaxes very quickly into thermal energy. Now, this of course puts us a bit in a problem, because in the synchrotron, we don't have this type of resolution. So we clearly had to go to the free electron laser. But above all, we also have to go to the free electron laser and not only measure X-ray absorption, we also have to measure the emission. Because while here you see this very nicely symmetric type structure, we have actually evidence that this is not that symmetric. So the holes and the electrons do not have exactly the same energy distribution. So you should measure both the emission and absorption at the same time to get the complete picture of what is happening on the carriers in real time. So that of course means that we had to figure out how to do RIXS at the free electron laser. And I think there is a very nice study that has a kind of a parallel why RIXS is important. Is the study from George Ivanko when he measured iron oxide, where he shows that when you have laser on and laser off, if you will only do emission or if you will only do X-ray absorption, you would actually lose part of the information. And this is quite clearly seen here. You have laser off signal of the iron oxide, you have the laser on, and then you see that the difference is not just across the main emission line or across one of the emissions. So RIXS clearly is the way to go to capture the entire information. But of course, that led us to the question is, how on earth are we going to do this in the free electron laser? Now, for some of you that have never done RIXS, the most common way to do it is, of course, you have either a dispersive spectrometer, and then you scan the beam, and then basically you will collect the spectra at every energy and you build the map, or you have a kind of a Jochen-type spectrometer and you do basically the same thing, but then you also have to scan the crystal. And then, of course, this means it's time consuming. Independently on the free electron laser, scanning the energy beam is really, I would say, impossible, just because it takes a lot of time, and they will definitely not give you beam time to do that. So it gets out of the question. So it became kind of clear that it's going to be tricky to do RIXS. The other thing is that at the moment, most of the experiments, or until quite recently done at the free electron laser, you needed monochromated pulses. And that also, of course, means that you will have a drop in the flux of the pulse itself, but most importantly, you have a huge broadening, temporal broadening on the pulse. So if you start with about 1 femtosecond, you will end up about 20, 30 femtoseconds. And if you go back to the time scale that we need to look at the plasmonics, the process starts basically through the London damping within a few femtoseconds. So we want to use the shortest, most intense pulses that possible. So it made us think, and I would have to say there is a lot more clever people than me on this, but especially with Jakob and Eve, we came up with this idea that what about if we use the non-monochromatized SA pulses, which are basically very, very, very ugly pulses. They have about 100 electron volts in energy. They will jitter like crazy, like any laser. But the idea was, if you collect the emission of all of this and you let the stochastic process take place, you should be able to reconstruct a RIXS map by simple matrix. And that's what we kind of proposed to do at the free electron laser. So we took a kind of a simulated SA pulses, which are quite ugly, both in energy and in jitter. We simulated what that X-ray emission spectra would look like. And if you then put this in a matrix, you are able to reconvert the RIXS map. The benefit of doing this is that if it works, you do not scan anything. That means you do not monochromatize and you don't affect the energy of the beam. That means that you get the highest flux and the shortest possible pulse. And at the same time, you actually build the RIXS map that contain all the information. So this is the setup that, that was put at the LCLS on the XPP beamline. We had to develop a crystal that would be almost 100% transparent, but not 100%. So we could actually measure what the spectra of the pulse on the shot-to-shot basis is. Then we have two Van Hamos to be able to cover the entire energy range to have the RIXS, so to have the K alpha and the K beta. And then you would have actually another kind of crystal with a high reflection to measure what is the pulse after the sample. We, of course, when you are at the free electron laser, you have to do this in a jet because it's a quite destructive beam. So you have to be able to refresh the sample. And I would say at the LCLS, when we did these experiments, we were running at 100 Hertz. We also got the shortest pulses that they ever gave. That was the 5 femtosecond pulses. And the jet, the normal liquid jet, is okay to replenish the sample. Of course, now with the new free electron laser in Hamburg, with a high repetition rate, a more advanced jet needs to be done in order that you actually refresh the sample every single shot. So this is how it looks like. This is a zoom of the pulses coming out of the free electron laser. I should say that they were so interested in looking at this because they never actually seen the pulse before on the kind of real time. And of course, the very ugly pulse when you talk about laser, and me working with optical lasers, you would actually be scared of seeing an optical pulse like this. But for us, this was great because if you have this jittering process taking place and you let the stochastic process take place, then you are able to reconstruct the map. And you can see by a simple matrix inversion, we were able to basically deconvolute both the valence to core, the K alpha, K beta, and also the X-ray absorption. And so I think what was important from this is, of course, there is a lot of things that now kind of spill over from this. From the physics point of size, I mean, we could see saturatable absorptions and we could see 2-photon absorption. But I told I'm a chemist. The real benefit of, I think, for a chemist in this perspective is that we are able now to use very intense pulses, very short pulses, and actually go there and do an experiment that we do not know the result. Because we know the electronic structure will be measured. And we know the signal is within the electronic structure. We don't know if it's in the absorption. We don't know if it's in the emission. We don't know in which of the emissions will be more visible. Maybe it's even a combination of all of them. But this is no longer a decision we have to make before we go there. We can just measure and then bring the data home, do the cuts, and look for the difference. So what do we want to do now with this? Now, this is a very long process. The paper was only published in December last year. Now we have the tool. We have the times that the free electron laser allows us to measure. So we should be able now to finally go back there and measure, for example, carrier dynamics. And that's quite important to actually go from this Loudon dumping that creates the hot carriers into a kind of a thermalized state, but still hot enough that you could extract the charges. This energy distribution of those charges, it's very, very crucial because, of course, if it's very, very low probability of reacting directly on that plasmonic. So we normally put this in semiconductors, but the thermalization of that carriers will determine which kind of carriers you can extract. And for example, on a solar cell, that defines what is the voltage you're going to get on the solar cell. But also in the chemistry, it will tell you what process you can actually realistically photocatalyze on that specific process. There is also other interesting things, is that most sensitizers have this kind of nonlinear behavior, but the plasmonics is by inherently a completely nonlinear behavior, because the process is so quick that one hot carrier will very quickly form other hot carriers. And that means there is a relation between the photon flux and the carrier's energy that we haven't yet been able to establish. Some of them are quite even unpredictable. I mean, we always think that as the photon flux increase, you go for kind of a second order behavior. But depending where you hit on the plasmonic resonance, if it's more intraband or it's really at the plasmon resonance, this behavior is quite different. So it's important to understand this, but you need basically techniques that will measure down to 5 or 6 femtoseconds. And the other thing that has come quite recently into this topic has been that what is actually happening to the plasmon process itself when exposed to an electromagnetic field. And this is actually something a little bit exotic for a chemist, but what we are basically doing is changing the electric and magnetic properties of these materials in real time. So there is a clear difference optically because you changed the electric property of the material. And that's how we see a change, that you have excited the plasmonic. But it has been shown that if you expose this to, for example, strong electric fields, the resonance also changes. And we don't really understand very well how this is happening and how this is going to affect, for example, catalysts and solar cells, because you will always be exposed to certain kind of levels of electric fields, something like this, when you have the material working. So even very small perturbations, I mean, if you, for example, put this in a slightly different surface, it will already have a change in the resonance. So the magnetic field, understanding of an electromagnetic field actually affects the plasmonic process itself is quite important. So of course, we have not yet data on this, but hopefully now with the tool and with people now being able at the free electron laser to get out of the energy of iron, we should be able to start being able to measure things like for example, gold. Of course, I have to say thanks to a lot of people. I mean, by no means the list is complete. And then, of course, there is the recurring name of Jakob, since we developed most of the things together. But of course, here I want to point out Eve and Wojciech, which have done quite a lot of work. Marcus Lundberg has done quite a lot of work on actually making sure that we extract data of non-damaged beam. And I on purpose left that out, since Julie is going to talk about this on Thursday. I'm quite curious to see what she sees the threshold for beam damage at the free electron laser. And then of course all the team of the XFEL, which has been very central to the development of this, the people at LCLS, both Dilling and Roberto, and of course we are also trying to move some of this into the Eli Prague, which is a laser-based thing, which would have a perfect synchronization in terms of thing, which is still something that is quite problematic at the free electron lasers due to the problem of the jitter of the XFEL compared also with optical. And that's about it.
All right, wonderful. Hey, Evan, do you want to ask your question? I see you've got one posted. I'll go ahead and paraphrase the question. During Landau damping, how many electron hole pairs are typically formed, and how does that number compare to the number of atoms in the probed element?
This is something we don't know. It's really like, it's a very good question. I mean, and there's people that describe this slightly different, but I think probably the description from Naomi Alles and Peter Nordlander at RIXS, which we work with them, and is that at the beginning, you can really treat this as one electron being excited. But very quickly, this electron will collide within this electron gas and form other electrons. On the process, on the beginning, is even kind of elastic process. So it's you really form a lot of carriers, and it depends basically how does it collide. Does it collide within the gas, or does it collide at the interface? So this is still a very big open question. And of course, for solar cells and for catalysts, this is essential because electrons and holes are basically our reagents. So we need to know how many of those reagents we have and how much energy do they carry. So being able to look at the London damping in real time, it's gonna finally answer the energy distribution. Now, and also the quantity that they have. But the other important thing is that it seems to be on the beginning that the electronic structure of the metal is quite crucial. So for example, for gold, it follows very well the electronic structure. How did you occupy these empty states? But on silver, this is a little bit, I would say, maybe not true. And silver in this case is actually the holy grail. If you can do it from silver, not because it's cheaper, but silver has a much better plasmonic. So for example, the solar cell company that I have uses silver, and the efficiencies are significantly higher that you compare with gold. So all of this is unknown. This has been simulated. Now it is to the last part, to the number of atoms. It is true that you have a minimum number of atoms to be able to sustain a resonance. So if you go anything below 2 nanometers, it's too quantized and you actually cannot sustain a resonance. So it's basically almost like a semiconductor type excitation where you put the electrons in very specific places and they don't resonate. But what is the relation between the number of atoms and the number of hot electrons? Again, it's not known. People think it's more related to the surface number of atoms that quantify the number of electrons, but it's not known.
Good. Here's another question. How small are the particles, and is there a difference between surface and bulk plasmons? Is there an effect from solvent?
Yes. So the goal, generally, we use particles between 6 to 10. And that
nanometers, 6 to 10 nanometers. Okay.
Yeah, 6 to 10 nanometers. But the resonance shifts. I mean, it's not as pronounced as in silver. If you have these changes, you would shift maybe like 30, 40 nanometers on silver. On gold, you only shift about 15. So but if you put the same particle, for example, on the titanium dioxide, or you put it on another semiconductor, the number of carriers and the dynamics of the plasmonics measured on optically are completely different. So the solvent and the interface where you put in the plasmonic is crucial to determine the charge distribution. There is I know I miss his name, from John Hopkins, is a very controversial person. It's a theoretical person, and he's actually shown that if an electron that is in the gas colliding, for each electron, it will generate another 2. But if it collides at the interface, it generates 4. This is the same thing valid at the surface. And the process on the beginning is primarily a bulk process, but it very quickly moves into the surface, primarily the electrons, because the mean free path is quite large for the electrons. In this case, that's been estimated almost 100 nanometers that you can still have mean free path of electrons. But most of these particles are on the region of, I would say, 5 to 30 nanometers. So the electrons are very quickly at the surface, and basically the process is all controlled then by the surface dynamics.
Okay. A last question concerning beam damage or saturation is maybe the more relevant thing here. What efforts did you take to check that you were in a linear regime with respect to the X-rays?
Yeah.
And I'll just comment also that in the XFEL studies we've done on nanophases compared to bulk phases, we find that the nanophases are more resistant to X-ray induced hot electron effects because of the escape length of the hot electrons. But what was your experience?
This is exactly also what we saw. I mean, we for example, you could run the sample for a lot longer with the iron oxide that you could run, for example, with the iron cyanide. The one process that we saw that has been disregarded on the paper that we published in this structure dynamics is actually ionization of the solvent that then induces ionization on the thing, and that happens in a much faster time scale that people have associated of beam damage. Electronically, of course, you control by the core whole lifetime. Anything above that, then you have to analyze. So what we did is, for example, we did experiments with different focusing. So we could focus the beam at the beginning of the jet or actually passing through all the jet. We also could attenuate the amount of flux that we had. So we spent quite a lot of time actually to try to get these thresholds between, for example, single photon and multiple photon absorption and have this saturation process. In terms of damage, I think what was really, really nice for us is that you could use the emission actually to track damage in your sample, which is quite nice. So if you are able to be able to measure one of the emissions that is not very sensitive for the chemistry or that you're interested, but is sensitive for the structure that you have there, then this is a very good reason to measure RIXS, because even if you don't need the RIXS for anything else, this allows you to say you are under this intact conditions, and the data you're extracting are really data associated with your chemistry, not something else that is happening due to beam damage.